welcome back to a new recording. In this recording, I'll be talking about geometric isomer. Guys, we have got two types of isomers in organic chemistry. One we call as structural isomer, the other as geometric isomer. Today, I'll be talking about the properties of those structures, the requirements in order to form a geometric isomer. What are those conditions for a structure to meet in order to form a geometric isomer? Prior to that, let us define the geometric isomer, guys. The geometric isomer are isomers in which the order of atom bonding is the same. That means the structures they have the same bonding order, but the different arrangement of atoms in space. The atoms arrangement are different in space. In another statement, we can say that they are having the same name of the parent, what we mean, same molecular but formula different orientation in space. We call as cis and trans. We'll be talking about those two types of geometric isomer. Guys, the geometric isomer, what are those conditions for a geometric isomer to for a structure to meet in order to form geometric isomer? Uh, Here we'll be talking about the geometric isomer and then the conditions as well. For the geometric isomer, the first condition is it must contain a double bond. So only for double bond structures, which we mean the alkene, they will form only the alkenes. They will form geometric isomer. The single and triple bonds, the alkane and alkynes, they will not be able those structures to form geometric isomer. Why only the alkenes? Because, guys, a geometric isomer needs a fixed bond which be away from rotation. That's why double bond prevent free rotation of carbon atoms. It's the reason why the geometric isomer can be formed for a double bond or a structure that contains double bond alkenes. And the carbon atom in the rigid structure which have two different groups attached. The second condition for a geometric isomer to be formed, each carbon atom which they bonded by double bond, they must attack two different groups of atom. This B, A, B. So as we can see, the first carbon here attacks to two different molecules. A and B are different from each other. The other one, A and B, they are also not the same atoms or same groups of atoms. That's the second condition for a structure to form a geometric isomer. And guys, whenever the same uh, type of the atoms are in the same site, like in this structure, A and A are in the same site, we will add a prefix of cis to the name of the isomer, and then if they are in opposite sign, here we have got the opposite sign R to the R, H to the H, we add the trans prefix for the isomer. As you can see in this structure, the R's are in the same side. That's why an H in the same side. That's why we have used the C's to the structure, and then in the other one we have got opposite the same molecule, the same type of the groups of atoms. That's why we have used the trans. And the third condition is what, guys? At least one of those group must be the same compound or the same group of atoms. At least one of those groups must be the same group. What we mean, we will be providing, let me provide an example, guys, to that in order to understand what do you mean by the third condition. Guys, here we have got two double bond, two carbons, they form a double bond. If we have got A, B, C, D, As you can see, this structure meets the first and the second condition. How the first and the second? For the structure, we have got double bond, so this is the primary condition. And then the second condition is each carbon attached to different atoms, A, B, and then the other C, D. But do we have any atoms that are the same? No, this won't form a geometric isomer because of one of the at least one of those groups must be the same. These are the three conditions for a geometric isomer, for a structure to form a geometric isomer. Let us provide examples and name those examples as well. Guys, here we have got a structure. This structure, let us name it according to the IUPAC system and check whether it forms geometric isomer or not. First, we have got double bond. It's the first condition. The second is double bond. This hydrogen bonded with the hydrogen and chlorine, and then the other hydrogen and chlorine. And the third, at least one of those groups are the same. Yes, in this case, both groups are the same. And the same type of the atoms are in the same side. That's why we have to add a prefix of C's to the name of the structure. This is the geometric isomer, which the type of the cis geometric isomer because of having the same types of atom in the same side in the structure. And then we will provide the position for the carbons according to the double bonds 1 2, or you can say 1 2, has no problem because in both sides it's the same. And then 1 2, how many chlorine do we have? 2 chlorine. So on the both atoms of carbons we have got chlorine, there should be a prefix of di because to chlorine we use the prefix of di. And dichloro, what's the name of the parent? Ethene. This is the name of the parent. For the other structure, guys, we have got the same group as the same type of atoms opposite to each other. That's why we add on instead of cis the trans. As you can notice, the only difference is the cis and the trans, and the name of the structure for both types or for both geometric isomer are the same: 1,2-dichloroethene. Let us provide more examples and practice more more structure in order to know which structure won't produce geometric isomer, which will produce geometric isomer. Have a look on these structures. Why these two structures they would not be able to form geometric isomer? Because as you can see here, there is no double bond and this carbon attached to the three hydrogen, so it won't form a geometric isomer. It has no conditions of geometric isomer. The other one, there is no double bond, and then this carbon attached to two hydrogen, one chlorine, two hydrogen, one chlorine. There is no double bond. That's why it has no tendency to form a geometric isomer. These are the requirements in order to form a geometric isomer. Guys, to let us test the following. Here, let us see if it forms a geometric isomer or not. Here we have got double bonds, and this carbon attached to the same atoms, it won't form a geometric isomer because the carbon should attach to the two different atoms. The other one, the same, double bond exists, but the carbon attached to two different to the same chlorine, and then the chlorine here attached to the same carbon. That's why it won't produce a geometric isomer. Here we have got a note: there is no double bond, but left side carbon atom contains same element, so no geometric isomer. If we have got no double bonds in the structure, it won't form geometric isomer. But despite of having double bonds in the structure, there is possibility to not form geometric isomer if the carbon attached to the same group of atoms. Or finally, if all the atoms are different, there is no groups of atom that attach to two different carbons are the same. Guys, let us practice more questions in order to know how uh, to be prepared for the ministry exam in the geometric isomer. It said, draw the structure of isomer 2-butene, label with cis and trans. The butene is four carbons, so there should be four carbons: one, two, three, and four. And then on each carbon, here we have got a double bond, and then it forms four three bonds with the other carbons. There should be an hydrogen attached and hydrogen attached. As you can see, the same hydrogens are in the same side, which is cis 2 butene, and then here the hydrogens are in different side, or the ch3 are in different opposite to each other. We use the trans 2 butene. The only difference is the trans and the cis. Guys, let us solve more questions, more examples to be prepared well for the ministerial exam. Which one is wrong for a given structural formula? Guys, said geometric isomerism of C4H8. Let us see if we have C4H8, C1, 2, 3, 4. This is C4. And then we have got 3 plus 3, 6 plus 2, 8. This is true, guys. But he said which one is wrong? C is 2-butene. The structure is cis-2-butene? Yes, it's cis-2-butene. A and B are correct. Is that alkene? Yes, it's alkene. No geometric isomerism. There is geometric isomer. So the D is a correct answer for the wrong, which is wrong option. It forms geometric isomer. Why? Because we have got double bonds. Each carbon atom that they form a double bond, they attach to two different groups of atoms, and then at least one of those groups are the same. Let us examine the other one. Which one of them has geometrical isomer? There will be such questions in ministerial exam appeared. Such questions, such type of questions that said, which of the following will form geometric isomer or will not form geometric isomer? The conditions, the three conditions, if a structure meets those conditions, it would form a geometric isomer, but if not, it refuses the structure to form a geometric isomer. Let us draw this structure. Prior to that, guys, those parentheses, they ended with the ANE and YNE, we have to cancel out. Because the single bond structured and the triple bond structures are they won't form geometric isomer. ANE, so it's cancelled out. YNE cancelled out. AC are cancelled. B and D. Guys, B and D, let us draw the structure for B, which is one butene, one, two, three, four, and then the double bond is in the first carbon. It's CH2, CH, CH2, CH3. How to know whether this will form a geometric isomer or not? Because, guys, there should be conditions. What are those conditions? We mentioned the conditions. We will be working on the carbons which they form the double bond. Open the carbon hydrogen atoms, carbon attached to the other carbon by a double bond, and then this carbon here attached to two hydrogen atoms, and then the other to a hydrogen with the CH2, CH3. Guys, as you can see here, this carbon attached to the same hydrogen, the same groups of atom, so it won't form geometric isomer because it attached to the same type of atoms. About 2-pentene, or let us check for, test for the 2-pentene. Here we have got a note about B, guys, said for unbranched alkene, this is for unbranched, it's not useful for branched. If double bond is on the first carbon, there is no geometric isomer, such as one butene, one hexene, one heptene, and so on. If the double bond for straight chain hydrocarbons of alkenes are in the same carbon, it won't form geometric isomer. Just keep in mind as a note. And then we have mentioned, we said ending with the ane and yne, there is no geometric isomer. We can cancel out them. Uh, uh, because they won't be able to form geometric isomer. Let us examine the D, guys, to know whether it will form geometric isomer or not. I will be drawing the structure to show you how to uh, test whether a structure will form a geometric isomer or not. Let me draw the structure for 2-pentene. Pentene is 5, 1, 2, 3, 4, 5. On the 1, 2, 3, 4, 5. On the second, we have got a double bond, and then here we have got CH, CH, H2, H3, H3. The one that we will be considering to test the geometric isomer is the carbon that formed the double bond. Guys, let us draw the expanded structure. This carbon attached to hydrogen and in another end CH3, and the other carbon to a hydrogen and in another end CH2 CH3. As you can see, let us provide the conditions. First, it has got double bonds. Second, this carbon attached to two different groups. The other as well, two different groups. And third, at least one of the group is the same. Hydrogen and hydrogen is the same. That's what geometric isomer. That was all about the geometric isomer. Thank you for the attention and hope it makes sense for you guys.